BrO4 minus, that's going to have 7 plus 4 times 6 electrons, and then an extra one for the -1 charge. So that's 24, 25, and 32 electrons. Right? All right, so let's put them together. Br, O, 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 and O. That's used up 8. So 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So like that, right? But what's the problem with that? Is there any problem with this? Of course, we haven't figured out the formal charges. But hopefully if we do that, we'll find the issue here. So the formal charges here, the oxygens are going to be -1 each. And the bromine is going to be +3. So that works out in terms of the overall charge. You've got 4 minus and 3 plus, but we really never see a formal charge of +3. And the fact that there's so many formal charges everywhere is a clue that this is not the best structure. This is a structure, but this is not the best structure. So we should not just leave it like that and say that the formal charge should be on bromine should be +3, because that really is not likely. Let's minimize the formal charges in the same way that we did with some of those other structures last week, recognizing that bromine can have more than an octet. So we can bring down some double bonds from the oxygens, like this. That will still leave a negative formal charge on that one oxygen, but then everything else has 0 formal charges. So that's a better structure, and that's why the answer here should be 0. All right, that's how these questions can sometimes be a little bit tricky, especially on the final. They'll give you a structure that seems like pretty simple, and you're in that kind of crazy final exam mental state, and you're like scribbling down structures as best you can, and so you just get a structure, you say, great, this structure has this formal charge, that's one of the answers, I'm going on. But make sure that you're really asking yourself, okay, is this the best structure? When I draw a Lewis structure, is this the best Lewis structure for this molecule? And so that should lead you to that answer. All right, same issue then, I would imagine, in this other one that was the next most widely missed problem, which was this one. And this was actually an example that we did in class last week in the notes. Best Lewis structure for SO4. It's essentially the same issue. You can draw a Lewis structure for SO4 that looks like this one. That's kind of the first one that you come up with when you distribute all the electrons. But that gives you lots of formal charges. If you bring down a couple of the oxygen electrons and make double bonds over here, you zero out those formal charges. And so this one is the better choice. Whoops. Sorry, not that one. Doesn't have enough electrons on the oxygen up here. I meant this one. That one's a better choice. So you see that? So both of these structures, this one and this one, are correct Lewis structures. They're chemically correct. They show the correct things. They fit octet rules where they need to be fit. That's fine. But the bottom one is considered a better Lewis structure because it minimizes formal charges. Now, as we get into some other stuff now in the next chapter, we'll learn that that actually may not be the best structure because it may not be the most accurate representation of that molecule, and there might be better ways to do that. But in terms of the rules we've been talking about so far, that's the better Lewis structure. One key with these formal charges, you really have to do enough of these practice problems that you don't have to sit there and add up every formal charge and every atom every time. The final, in particular, is quick. It's 40 questions in 60 minutes. So it doesn't give you a whole lot of time to really do that. If you do enough practice with these, like I was kind of doing here, you'll know every time you see an oxygen with a single bond, and 6 electrons around it, it's got to be a -1 formal charge. Every time you see an oxygen with 2 bonds, it's 0 formal charge. So there's like some common ones that come up again and again, and the more you practice this, the more you'll just see it, and you won't have to go through that equation every single time for every single atom, and it'll make you a lot more efficient at doing these kinds of problems. All right, do we have any other questions about the quiz or other problems you want to see done or gone over? Okay, yeah. Number 7. This one? Only when I get to it because the numbers are not on this thing. This one? That one? That one? All right, so this one, again, the best Lewis structure for sulfur, or for SO32-. Couple things with this. First of all, some of these have actual problems, like the Lewis structure is wrong for some reason. Like, I'm trying to think of. I guess that's not true. All of these are technically correct Lewis structures. I guess this one isn't because of the more than an octet on oxygen. The other 3 are okay octet-wise and electron-wise. So really the question should be, which is the best or most descriptive Lewis structure for SO32-. The problem with the first and third one is, again, the formal charges. So in here we have minus, 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 and plus. That's a lot of formal charges. And this one down here, we have sulfur with a 2- or -2 formal charge all by itself. And in these, we have just oxygens with negative formal charges. So minimizing the formal charges and keeping the negative charges on the more electronegative elements tells us that that second set of structures is the best. The reason it's drawn as 3 structures like that with those double-sided arrows is because of resonance. So that's just showing that there are actually 3 resonance forms to this structure. Yeah. Any other questions or concerns about these? Okay. Let's move on. Oh, yeah, I put that up to remind me to talk about the lab tomorrow. Whoops. Okay, before we get into this, I forgot one more thing. I wanted to briefly talk about at the end of this set of notes that we went through last week. I don't want to get too much into this because it's really not that crucial. But one of the ways that we can think about these bonds is through the energetics. How much energy does it take to break a bond, or how much energy do you give off by making a bond? So bond formation is exothermic, bond breaking is endothermic. So what you can do is you can say, well, okay, to make a methane molecule, that's really like 4 individual CH bonds. So we can look at how much energy it takes, the change in energy from losing an electron, or losing a hydrogen each time, losing one of those bonds. And the total change in energy there should be what we call the heat of formation of methane, or the potential energy of methane. Now, different bond energies have different values. You do not need to commit these to memory. But you should have a basic idea of the ordering of these relationships. Some of them are pretty straightforward. A double bond is higher energy than a single bond. That means it's stronger. Triple bond, stronger yet. That makes sense, right? The more bonds you have, the stronger that interaction is going to be, or the more energy it takes to break those apart. A CH bond is a little bit stronger than a CC bond. And a couple terms that we are going to get into more in the next chapter is that you've probably heard before, sigma bonds versus pi bonds. When you have just one single bond, that's called a sigma bond. And when you have 2 pairs of electrons, you usually have a sigma and a pi at the same time. We're going to see what those look like when we get into the molecular shapes and kind of the orbital shapes and what that all gets to. but we'll get into that. So the idea here is that you can kind of correlate bond strength and length, and you can make a guess as to the overall energy of the reaction, whether it's endothermic or exothermic, by adding up the bonds broken or formed on either side. So in this particular example, we've got hydrogen and fluorine equals 2HF. Another way to think about that is we have to break up a hydrogen molecule, we have to break up a fluorine molecule, and then we form 2HF bonds. You see what I mean by that? So it's like you're breaking all the reactants into their constituent elements and then putting them back together as the products. That's not really what's happening, but the energies will work out that way to an approximation. So you can say the change in energy overall for this reaction is going to be the bonds that we have to break, the energy of the hydrogen bond, the energy of the fluorine bond, and then subtract the energies of the bonds that are formed. So you do that and you get minus 544 kilojoules, which tells us that this is an exothermic reaction. That negative number that you get means that that's heat given off. And that's really all it is. You look up the bond energies, you use a positive sign for the ones on the left, a negative sign for all the ones on the right, and then you add them together, and that's the overall change in heat for the reaction. So there should be some problems in Chapter 9 that you can practice, kind of like this one. It's really nothing tricky, and you don't need to know any of those energies in your head. If you had to do this, you'd be given a table of those bond energies. And it's just as simple as adding them up, adding the ones on the left, adding the ones on the right, and subtracting. So that was kind of the end part that we didn't quite get to. Okay. Let's get into some interesting stuff. We talked now about Lewis structures, so everybody's good with drawing those structures. The next step is figuring out the shapes of the molecules. When we've got the structures, we've got the shapes, we've really got a good model for what this thing really actually looks like. And if you think about it, that's a pretty powerful idea, that we can take something that we really can't see, we can measure but we can't see, and we can predict what its atomic or molecular shape is going to be just by some relatively simple rules. So the main model that we're going to use right now is called the Vesper model, which really is spelled Vesper. It stands for valence shell electron pair repulsion. And the important thing about that is the theory is that the structure is determined by electrons repelling each other. We know electrons are negatively charged, so they're going to want to be as far from each other as possible. That's really the whole theory. Electrons want to be as far from each other as possible on a molecule. Now that includes electrons that are lone pairs, those non-bonding pairs of electrons, and electrons that are in bonds. So all of those things are going to spread out as far away from each other as possible. And that's essentially this theory. So we would say, let's say a molecule like BeCl2. That's pretty simple because it's just got two things. But the Lewis structure is like this. Remember, beryllium is one of those weird exceptions that has less than an octet. The structure says, well, this should be a linear molecule, meaning in a line, because those chlorines, or more specifically, the bonds between the beryllium and the chlorine, want to be as far from each other as possible. And putting them on opposite sides is as far as they can get. Anywhere else you put those two, they're going to be closer together than being opposite. Do you agree? Believe that? Okay, good. If you find another way that they could be, great, but I think you'll find that one. So that bond angle is 180 degrees. Right, that angle is 180 degrees. And so this is how we're going to step through it. We're going to look at each grouping of different numbers of things attached to a central atom, and then what kind of shape do you get when they all spread out as far apart from each other as possible. So BF3, we often write it like this when we're just looking at Lewis structures. But that's not really the shape of the molecule, because those fluorines, or those bonds between the boron and fluorine, are really closer to each other than they need to be. They're the angle right here, for instance, It's a 90-degree bond angle. And that means those things are relatively close together. An alternative structure and a better structure is what we call a trigonal planar structure, where we kind of imagine a triangle and the boron in the middle of the triangle and the fluorines at each corner of the triangle. So like that. That's a better structure. It's still flat. That's a better structure because this angle is now 120 degrees. So you've moved those things further apart from each other, which means any structure where you have one central atom and three things attached to it is going to spread out so that the three things are kind of at the corners of a triangle, because that puts them farther apart from each other. Good so far? Maybe? Okay. Next, we got the tetrahedral structure, and that's going to be methane. Again, we usually draw, or we have drawn methane like this, CH4. You just draw your H's like this. There's no lone pairs. But that is not the farthest that those things can get spread apart, because again, we have 90-degree bond angles. Now, if that structure stays flat, then yes, that is the furthest apart they can be. But these are three-dimensional molecules. They don't have to stay flat. So that means that this structure is really going to be a three-dimensional structure. And the way we draw it, there might be models in here. Should grab one. The way we draw it is like this. Now that that kind of wedged bond, that darker bond, is coming out at you, and the dashed bond is going back into the paper. And that type of a shape is called a tetrahedron. It's a regular solid, meaning it has sides and sides the same. I'm not going to draw it super evenly here, but it's basically like that. Kind of like a pyramid with a triangular base. So every side is the exact same. And the hydrogens are at the corners of that, and the carbon would be right in the middle. And that's known as a tetrahedron. And in that case, the bond angle is 109.5, or about 110. So that spreads that out even more than 90 degrees, which is what it would be when it's flat. So any molecule that has four groups around a central atom is going to adopt a tetrahedral structure so that the repulsions are minimized. All right. So this steps to apply the Vesper model. You can look in your book for like the specific instructions, but it's basically what I just said. You figure out how many groups are around the central atom. You distribute the things accordingly, then you figure out the shape. So let's look at these four. Of course, methane we just did. We say, okay, methane has four groups around a central atom. And so it's going to have this tetrahedral type structure. Now let's look at ammonia. If we just look at that molecule NH3, it looks like, well, there's three things around the central atom. And so this should be a trigonal planar structure. But it actually isn't. And you know why? What's different about the ammonia structure? Well, let's look at it together. There is, but it's actually from the non-bonding electrons. So if we draw a Lewis structure for ammonia, just keeping our 90-degree bond angles because we're not sure what it is yet, we end up with a lone pair, or a pair of non-bonding electrons, on nitrogen. So that means that there's actually four groups around that central atom. The way the book describes it, they split it up into two categories: electron groups and atom groups. Electron groups include bonds and non-bonding pairs. Atom groups are only the atoms. So the geometry, the overall molecular geometry, counts both the lone pairs and the bonds, which means this really has four things, so it should be a tetrahedral structure. And what we might draw is we can kind of put the lone pair on a bond like that. And so this is still going to have that pyramidal type structure, but the electron pair is going to take up one of those spots. And then the same thing happens with water. If we draw water, this is a Lewis structure, regular old Lewis structure. There's 2 lone pairs on that central oxygen. So this is not a 2-group type structure. It's not linear. I mean, we know it's not linear anyway, but the hydrogens can't be linear because we have to include both of those lone pairs in the structure. So that means water is going to have kind of a structure like this. And you can put these lone pairs any way you want. And that's really the structure that we know more of water, where it's kind of bent with those hydrogen atoms. Let me see. I don't know if this computer has it. Let's see if I can show you a 3-dimensional version of this. Yeah, this will work. So I'm going to draw that that methane molecule. And as I draw it, the 3-dimensional structure pops up over here. So now I can find my tool. Oh, I gotta go over here first. I can rotate this. And so this is what that structure looks like. It's a little bit hard to visualize with the dashes and wedges. But if you see the one going up, one going kind of off to the side, and then one coming out at you, that's that wedge, and one going back, that's that dash. All right, if we kind of rotate it around, back and forth, you can see, kind of get a sense in your head of what that structure looks like. So if 2 of those end up being non-bonding pairs, lone pairs, then we can see how the other 2 atoms have kind of that bent type geometry that we see in water. Yeah?
Does it matter which one will be the lone pair?
No, this is a totally symmetric structure.
Let's say like it was like oxygen. Does it matter which one? Lone pair, like in the back?
No, they're all symmetric. They're all the same. They're all equivalent. So like if I went like this, you don't know which position is which anymore. So no, it doesn't matter. You put them wherever you want to put them. Okay, so let me stop that. What does this do? All right. So those are our structures. Now, would we say then that these are all tetrahedral? The answer is no, we don't. They all have a tetrahedral geometry, which means they all have roughly 110-degree bond angles. We'll see that it's a little different from that, but roughly those same bond angles. They all come from the tetrahedral structure, but we don't actually see lone pairs. They don't actually take up a space on a bond like that. When we look at water, it has kind of a bent or a V shape. We don't say it's tetrahedral shaped. So we have these different names of shapes. Trigonal pyramidal, which is what this one would be called, kind of like a triangle pyramid, not exactly a tetrahedron. And then H2O we call bent or V-shaped because, again, that's different. We only see the atoms. We don't see the electrons. So that leads to 2 different categories. Was my table not? Oh, there it is. And we'll go through all of these, but I wanted to show you that there is a table that summarizes all of this in your book in chapter 10. Let's just look at the ones we looked at so far, which is this middle block right here. So these all belong in the tetrahedral geometry category. They all have that same basic structure when you include the lone pairs. And that's because they all have 4 what we call electron groups. How they differ is by what we call bonding groups, the actual atoms that are bound, like the number of bonds. So the electron groups determine the overall geometry, like the bond angle, but then the bonding groups or the atom groups determine the molecular geometry. So if we actually want to know the shape, if you hear terms like shape or molecular geometry or molecular shape, you're going to use these types of words because that's really what we see. So tetrahedral, trigonal, planar, and bent. We wouldn't say those are all tetrahedral, But we would say they all have tetrahedral bond angles because that's what they originally come from. Right? And this is true for any number of electron group categories. So let's go through and look at a couple more of them and look at some of the other issues that come up. Well, first of all, when you have those lone pairs, they affect the bond angles a little bit. So they start around 109.5, or I say about 110 because we don't really need that much precision. But the fact is that ammonia, the bond angles are a little bit smaller, 107. And then in water, the bond angle is a little bit smaller still, 104.5. All right, and the theory behind that is that the lone pairs kind of repel more than the bonds do. So the lone pairs on water, back up here, I'm missing a page, will actually push those hydrogens together more than they would be if they were in a perfect tetrahedron. So when you see the lone pairs, you can expect that the other bond angles are going to be a little bit smaller than they would be otherwise if everything were even all the way around the molecule. Okay. So let's look at some larger structures. We looked at the linear, trigonal planar, and tetrahedral. And now let's look at the trigonal bipyramidal structure. That's what happens when you have 5. So now we're in this expanded octet. PCl5, for example. This is probably the most complicated structure of all of them because it actually has 2 different bond angles. There are 2 atoms in a trigonal bipyramidal structure that are linear, kind of like straight up and down. And we call those axial. And I'll label that in a second. And then there are 3 more that go around the middle in a trigonal planar structure. Like that. So the angle between these 2 is 120. The angle between these 2 is 90. The ones on the top that I've got in blue are called axial, and the ones around the middle are called equatorial. So the axial atoms on the axis and the equatorial atoms around the equator, around the middle. I don't know if we can get that one in 3 dimensions, but let's try. Oops. Freaking everything out here. So there's P. That is not the right structure. Let me see if I can do that. I forgot how to do this. Just try that one. All right, so it's giving me a planar structure, but it's not right. Let's see if we can throw this out of whack a little bit. So I'm trying to do a calculation to minimize the energy. There we go. But it was already too far away from correct, and that's why it didn't work. So here's the correct structure. So you can see that here. You've got those chlorine atoms around the equator, and then the axial ones kind of up and down. And those ones around the middle are in a plane. Okay. Now, let's see if we have that here. Let's look at what happens when, how much time do we have? Yeah, we'll just stick with this. Let's look what happens when we end up with lone pairs in those types of structures. So one example of this is SF4. If we draw a Lewis structure for SF4, we get four Fs and then 2 extra electrons on the sulfur. Like that. So that tells us that's technically 5 electron groups, the 4 fluorines and the 1 lone pair. That means that that 1 lone pair occupies a spot, so we're going to have a trigonal bipyramidal type geometry. This is the only structure in which we have to actually pick where the lone pair is going to go. All the other ones, all positions are equal, so you just put the lone pair on one of them, it doesn't matter which one. But in this one, the positions aren't equal. If the lone pair goes on an axial substituent or axial position, that's going to be different from the lone pair going on the equatorial position. So which one do you think it goes on? Which one's going to minimize the repulsion? Remember, things want to be as far away from the electrons, from the lone electrons as possible. So what puts them furthest away? The electrons being at the axial position or the equatorial position? Who says axial? All right, who says equatorial? So let's look at it. We can figure it out from the bond angles. If the lone pair takes the axial position, then it's 90 degrees away from these 3 and 180 degrees away from this one. If it takes this position, it's 90 degrees away from these 2 and 120 degrees away from these 2. And it actually turns out that that's better. Being 90 degrees away from 3 of them is not as stable, is closer than being 90 degrees away from 2 of them and the 120 degrees away further down. So SF4 takes this kind of a structure. Oops. Lone pair goes over on this side. And the fluorines go over here. And this is actually called the seesaw structure. It's hard to see that, but if you imagine it kind of laying down on those 2 angled fluorines, it could like tip back and forth like a seesaw. Yeah.
How do you know that it goes in the middle part?
Because that minimizes the repulsion. Because if it goes up on the axial one, it's closer to those fluorines. If it goes on this one, it's further away from more of them.
Does that apply to all?
That always applies to this trigonal bipyramidal structure. It doesn't matter for any of the other ones because they're all symmetric. This is the only one where you have to make that choice.
Would they always be equatorial?
Yes. So the lone pair takes the equatorial position. And as you might expect, it actually kind of pushes everything else away a little bit, just like the other ones. So in that ideal structure, let's see if we can see this in the simulation here. If I make these. See if we can minimize that without screwing it up again. Now we screwed it up again. I'm not sure what the setting is to make it calculate more strongly, but we'll try this. Okay, so the program's not that smart. It doesn't actually know that there's supposed to be a lone pair there. We probably have to put it there. Let's see. I don't know if that makes any difference. There's also the possibility that this just can only deal with organic structures because that's usually what we use it for. Yeah, so we're not going to be able to see that. This program doesn't, or we don't know how to tell that program to do that. So you just have to take my word for it that that's how that works. If you can see, if you cut one more down, you'd end up with this T-shaped structure, and then finally you'd end up with a linear structure if you actually had 3 lone pairs. And there's an example of each of these in this table. So the other one we'll talk about next time is octahedral. The last 5 minutes I want to take a look at the lab for next week, or for tomorrow. This is another new lab that I have not done before, kind of like the Leaf lab, so we'll be working through it a little bit differently. The interesting thing about this one is we use our fanciest, newest piece of equipment in the instrument lab, inductively coupled plasma, which is this, as it kind of sounds, super, super, super hot flame. It's actually not even a flame, it's really plasma that we pass a solution through, and it excites the electrons in the atoms up into higher energy levels, and based on what kind of light is absorbed, we can measure what type of atoms are in there, and it's super precise. You can measure down to very, very small concentrations. This is the standard technique that's used in places like the EPA for measuring water and for measuring heavy metal ions in water. And so we're going to do that same thing. We're going to test water for things like silver, arsenic, lead, and iron and copper and those sorts of things. So the way that this thing works, it's kind of neat. Remember when we used regular UV vis last week? We had to make a calibration curve of the different dilutions. Same idea here, but you can do all the metal ions at the same time because the machine can actually sort them out. So instead of just a stock solution of each individual metal, which is how you would have had to do it in the old days with atomic absorption, you can actually take a cocktail, that's actually what they call it, of all these different ions as your stock solution, make some dilutions of that, and use that for the calibration. Then you plug in your unknowns based on that, and you can measure them very, very precisely. So we will be doing these. Oh, the other nice thing about that instrument is it can hold in its memory a calibration curve, and it doesn't really get screwed up. So rather than doing a bunch, than everybody having to do their own calibration and dilutions, we're just going to split the whole class into 2 groups. Each group's going to do 1 set of dilutions for the calibrations, and then you'll go run the instrument and do your water. So we want to have a lot of different water samples. So if you could bring some water in, either water from your house, water from a local puddle or something, or lake, something you see. If it's really dirty, we'll have to filter it a little and clean it up before we put it in the instrument, but that's fine. But just general drinking water, if you ever want to know what kind of minerals are in these drinking waters, or mineral water in general, like mineral waters that you can buy, or if you have some around, any kind of water that you want to test, bring it in, and we can check it out. And this is not just like a silly lab experiment. This is like the actual instrument that you would do this on professionally. So it will be a good, a really good reading of what's really happening there. So please look through this. If you want to look up the technique a little bit, there is also, I forgot to load it up, but there is a sheet on Blackboard. I just posted all this stuff on Blackboard, but there's also a sheet of the ICP schematic, like kind of how it works. It's not great. It's just this picture. But if you're at all interested in the technique, research it a little bit tonight as you're looking through it. There's no pre-lab, but just take a look at like what it is and how it works, so we can be ready for tomorrow. If you really want to get ahead of things, if you really want to be like the first group into the lab tomorrow into using the instrument, try to work out your series of dilutions. Each group will need 6 dilute solutions that use between 5 milliliters and 25 milliliters of the stock solution to make 100 milliliter sample total. So exactly what we did last week, but now with 100 milliliter total. And then we're going to assign each person an ion to focus on, and you're going to calculate what the concentration of that ion is in each calibration or in each solution, and then what the analysis was in the water. And we'll post all those data together. All right. Any questions about that for now? If questions come up, just let me know. But just take a look at it, read through it, and if you really want to get ahead, prepare. Figure out how you want to prepare the dilutions, and then we'll meet back tomorrow morning at 9:30 to do it. So thanks, and I'll see you then.